So, okay, so we're recording. Today it's week 14. We're getting close to the end.
True enough.
Yeah, I mean, only basically three more weeks. And that'll be that. After week 16, when I give you guys the take-home final, there won't be any, additional online presentations by me. It'll just be you guys submitting the final to the assignment or the project or whatever you want to call it, and that'll be that. So if you're tired of hearing me, you won't have to for too much longer.
Not really. I like it.
I know. I'm joking, but at the same time, let's face it, everybody gets tired after a while. So, all right, let's go through this and see what kind of trouble we can get into. I think most of this stuff is correct, but I'm not 100% sure as far as the work due. Well, it's due whenever you get it done by May 1st. So I don't want to spend too much time on that. So we're going to talk about threading today. Thread form, and all the qualities and nuances of thread forming, and how it, to interpret and call out a unified thread or a metric thread, and then look at some design tables to determine clearances and counterbores and for clearance holes, counterbores, and countersinks. So I don't really have to go through this stuff in too much detail about what fasteners are, but it's not just nuts and bolts. It is, it can be anything that basically holds two parts together. A press fit you could consider almost a fastener because those parts don't really they won't move. As long as the press fit is good.
Even a rivet would be a fastener.
Sure. Yeah, and they don't have it in this list here, but a rivet, a weld, a weld or a braze, or a solder joint is a fastener too. Yep. But we're talking about, in this, at least their description is some type of physical addition that goes beyond, just the press of two parts together, or a weld, which basically makes two parts one. Fasteners can be usually, they're considered fasteners because they can somehow be removed so that the parts can be separated. That's the other, I guess, key, even though I still look at welds and brazes and things like that as fasteners. They're permanent.
Right.
Right. So fasteners are considered removable. So we're either, when we're specifying fasteners on a drawing, we're either talking about threaded features or which are specified, as part of the design, and then general fasteners, which, if they're washers, keys, and pins and things like that, they're usually not on any kind of detailed drawing unless you're modifying it. They're just listed in a bill of materials or a list of purchase parts, so that they can be ordered and the correct style and size is there when needed. So we're looking at external, two types of threads for a fastener are either external or internal. So it says, in general, a screw thread is a ridge of uniform section in the form of a helix, which is true. The slide says that an external thread can be cut using a die or a lathe, which is correct, but it doesn't talk about thread forming, like rolling a thread, which is why I include those 3 videos, which I suggest whoever watches this video that you look at those videos also, and see how threads are rolled and what the difference between a roll thread and a cut thread is in terms of the quality of the thread and the strength of the thread with respect to the base material. An internal thread you can't really roll. So generally speaking, for nuts and anything that's got an internal thread, it has to be cut somehow. So that can be some kind of a limitation. And Bob, correct me if I'm wrong about that, but I've never seen a nut with a roll thread. But
no, I haven't either.
I don't. It seems to me that especially when you get into smaller diameters, whatever type of die you would have in there that you could roll, that you could possibly even try to roll that thread with, would not be very strong. Yeah. With the pressure that's required to actually upset the metal when you're rolling a thread, you would think that a die that would fit inside that hole would, even if it were supported well on both sides.
I think there'd be too much flex in the tool.
Yeah, the tool would crack because it has to be hard.
Right.
It has to be hard, and it's and there's going to be a lot of pressure on it. So, I think it's safe to say that any type of internal thread on a nut, for example, is going to be, even though the nut may be cold formed itself, the thread is going to have to be cut.
Mm-hmm.
Okay, so let's look at some of the components that make up a thread. Number one is the axis or center line. Two is the pitch. So the pitch is the distance between the distance between the threads. And it's interesting the way they show this, because this extension line, it shows in the middle of this particular thread. This one shows to the end of the flat, and I don't think that's correct. I think this should be, the pitch is going to be from the center of this thread to the center of this thread.
I would agree with that.
So I'm not sure who devised this slide, and I don't have any way really of modifying it that I know of. But so that's my take. There's one of the things to look at would be how it's displayed in the text, and then also look at the shop manual that you have with it, the little turquoise book, and see what they show for that dimension. And I think you'll find that the pitch is from center to center. So that's a bit of a oopsie right there. The crest, or the major diameter, that's where the major diameter is taken from crest to crest. The root, which is the smallest portion of the thread. And we're just looking at the profile right now, right? So this is the crest, this is the root. We'll talk about minor, pitch, and major diameters when we get to these right here. Number 5 is going to be the thread depth. And so when you look at this thread depth, it's the dimension is going from here to here. See how they did that? They used this dimension to not only display the minor diameter, but be the one of the dimension lines for the thread depth.
That's because of the formula for the thread depth is the major diameter minus the minor diameter. Right,
exactly. So, but I just wanted to clarify what we're looking at here, because for some folks that they're just learning about dimensioning right now, that might be confusing. But yeah, you're correct. So thread depth, number 6 is the minor diameter. So number 7 is the pitch diameter, and number 8 is the major diameter.
Right.
Number 9 is the side. Well, so, and 10 would be obviously the pitch angle. So though that varies depending on the style of thread. When you look at not an acme, but a straight thread, there's no angle, or their angle between sides is actually 0. They're parallel. It's a square thread. If you look at a square thread, not an acme, but a square thread, there is no angle. The two sides are parallel. It's a really strong thread, though. And if you look at a lathe, and you look at the shaft that has the half nut on it that you use to cut threads on the piece that's chucked up, those are the types of threads that are on that shaft are square threads, because they are strong, and they can be very accurate. So basically exactly what we looked at before, except a little bit of explanation. Pitch is the distance from a point on a screw thread to a corresponding point on the next thread, which kind of verifies what I was talking about in terms of that this dimension. It should be from the middle to the middle, or from this corner to this corner, which would be obviously the same distance. Crest is the top surface, roots the bottom. Depth of the thread is major diameter minus the minor diameter divided by 2.
Right.
You have to remember that. The depth of thread is not just the major minus the minor diameter. It's that result divided by 2. So the minor diameter is the smallest diameter. The pitch diameter is the diameter at which a line cuts the spaces and the threads equally. So when you go back and look at the pitch diameter, this is a point where, it may not look right. From depending on where you're looking at it, the distance from here to here should be the same as the distance from here to here. So it's the point at which that space and the thread are cut evenly. So it may not be exactly in the middle. It just depends on how the thread is formed. So if we're talking about the difference from here to here divided by 2, it should wind up that way. Like I say, sometimes it just does not look right. It does not look like it's right exactly in the middle, and it may not be. If you remember that this is the way it's defined, then thinking about it being exactly in the middle should be secondary. And then the major diameter, and obviously the largest diameter, the OD of the thread. The angle of the thread is the angle between the thread. The side is the side, and that's that. How about lead? Lead is the distance a screw thread advances axially in one turn. So would lead be the same as the pitch?
Probably.
Yeah, I think it is.
Yeah, because when you turn like a 1/4 bolt, you turn it 1 turn, you turn it 1/20 of an inch.
Right, exactly. It takes 20 threads in order to make a lead of 1 inch. So the or the ultimate lead of 1 inch. Right. So usually, and I'd say that knowing that it's a rock solid relationship. The lead and the pitch are of the same. And how about right-handed versus left-handed? We got a pretty good idea, right? Right-handed advances when turned clockwise, and that's a standard or a default. When you call out a thread or specify a particular thread size and pitch, that it's a right-hand thread. unless you want it to be a left hand, then you have to specify that it is left-hand thread. And left-hand thread advances when it's turned counterclockwise. The question becomes, why do we need left-hand threads?
Well, it's because if you have something that's turning right to the right and you're threading to the right, you have potential to unthread. Kind of like the arbor nut on a table saw, turns the opposite direction the blade does, so
Yep.
that it doesn't come loose.
Right, and the inertia of the blade moving in the direction that it moves basically tries to keep tightening up that nut.
Right, exactly. And of course, they're using the bicycle on the left-hand side, the same thing, the left pedal.
Right, and that is correct. That is correct. Left pedals on the bike are usually left-hand threads because the action of you pedaling the bike, if it were a right-hand thread, would try to
try and unthread it, and then
try to spin it out. Right, it would try to spin it out.
Going down the road with 1 foot on the ground and 1 foot on a pedal.
Right. Does anybody ever owned a car that had left-hand threads on?
Lug nuts.
Yeah. Right. Chrysler used to do that.
Yep, sure did.
I don't recall anybody else, but I'm sure there were others.
Mm-hmm.
And then they stopped doing it. I think because they finally realized that, well, hey, wheels weren't flying off any of the other cars that had right-hand threads on the.
And I think that originally there really was not a torque element on those nuts. Now they all have to be torqued like 100 foot-pounds.
Yeah, I think they do vary some, but depending on the design,
the size of the nut and bolt. But typically, most car lug nuts are 100 foot-pounds.
Yeah, well, I've seen them upwards of 120 foot-pounds.
Right.
I think a lot of it has to do with the design of the seat that's on the wheel. You know what I mean? The angle. So the angle of the seat, the material that the wheel's made from. Obviously, like you said, the diameter of the lug itself.
Right.
Because obviously you can't take a half-inch or a 3/8 diameter lug and crank it up to 150 foot-pounds or 120 foot-pounds. I mean, you probably can. It'd probably be okay, but might be on the verge of hitting the yield point. And if your torque wrench isn't accurate, you might over torque it, or if you don't use the right technique, you might over torque it or under torque it. So but a 3/8 diameter lug can handle the amount of torque that a 5/8 could. For obvious reasons, you got more area to spread the load across. Anyway, getting back to left-hand threads, the bike pedal is a good example of that. I had a Chrysler. I had a 70 Dodge Challenger, and the first time I went to change a tire on the left side, I broke off a lug nut before I realized they were left-hand threads. Left side or right side? I think it was the right side.
Yeah, I think
left-hand
it was too.
threads.
Yep.
Right side. Yeah.
Yep.
So common thread forms. There's only two, basically, either unified, used in the U.S., or metric, which is used in the U.S. and everywhere else, pretty much in the world, is on the metric system, except for us. Now, there actually are a couple other countries that still use unified or the ANSI system. They inches, pounds, feet, and what have you. We're not totally alone in the world in terms of the system that we use. So how do you choose a thread form? Well, according to this, what's the fastener going to be used for, length of engagement, and what types of loads will be placed on that fastener. And also the types of loading that that would be applied to the rest of the design. So, you know, for example, you know, in buildings, why do you suppose they rivet? And when they do the skeleton of a skyscraper, and you see them putting up all that steel, most of the steel is riveted together. Why do you suppose they do that instead of welding it all together? For example, you would think, you know, that would be stronger, right?
Yeah, it's less costly and just as effective. And all they're really trying to do is prevent that screw from backing out, or
Well,
that fastener from backing
yeah,
out,
yeah,
and spread the load.
that's true. They're trying to spread the load. Wouldn't a weld be better at that? Let me. I guess we're kind of digressing here a little bit, but when it says talking about loads and forces, when you look at, say, a beam that's and how a beam is supported, and you put a load on it, when you deflect that beam, you know, from the center, let's say you put a load on the center, if you have a solid connection to the points on each end, you're going to not only going to transfer the linear value of the load, you're also going to create a torsional element at those connections too. When you think about it, if you're pushing down on the beam in the center and it's supported on each end, when you push down on that, it's like a lever arm. So it's going to create a rotating load or moment load that on each end where it's supported, that's going to add forces to the to those connections. And we're only talking about, you know, small deflection, right? I mean, you usually can't have more than about 1/8 of an inch deflection in a steel form, whether it's an I-beam or a tube or an angle or whatever it is, before you're creating, you know, so much stress that the material might yield at some point. And I'm being general here, but if those connections were bolted or riveted on the end, you wouldn't transfer because the deflection is so small. You wouldn't transfer any of that torsional load to those end connections, because even though it's riveted and it's bolted together, if you deflect the end a little bit, there's going to be a little tiny bit of you're still only talking about a clamping force between the two members that are bolted together or riveted together. So it's friction plus the clamping force, and it's not going to transfer the I know it's maybe a little hard to grasp at first, but it's not going to transfer the torsional load from the reaction or the force that's being applied at the middle of the beam and the reaction at the end that creates that torsional moment. It's not going to be there when it's bolted or riveted. That's why they rivet them together. It's still going to take all the vertical and horizontal load, but you know that it's designed to take, but it won't add that torsional element to that connection. And so that's why they do that, because most of the, you know, almost all the loads that are applied, you know, are either vertical or horizontal in some way, and that's what those designs are meant to deal with. So that's the reason why. We're talking about a whole nother class here, and we don't want to get into that too much, but that's what happens. And you can look that up and see how close I was in my description, and or how far off I was. You know, it's again been a while since I have to think about that. Okay, so how do we draw threads in 2D? 3 basic ways that we can draw those threads: either a detailed view, which is a full description, visual description of what the thread looks like, or you can use a schematic, which is basically a simplified version of this to some degree. But when you do a schematic, these short lines are still supposed to represent the minor diameter. This is supposed to represent the major diameter, and the distance between the long lines or the short lines is supposed to represent the pitch. Or the way 99.9999% of the rest of the world does it is just a simplified view. And most of the time they don't even show this, which would be the taper off of that last thread or two. So they don't usually just end in one full thread, you know, at the end. They usually wind up, you know, with a partial thread at the end, partial thread in the beginning so that you can start it, and then a partial at the end so that you have something to, if you need to have the, you know, the bolt or the nut stop against. But usually they just show this line that represents from here to here the full thread of the full length of the thread, or I should say the length of full thread. Usually, you know, sometimes you show this chamfer on the end, but the length of full thread still is assumed to be from the end of the fastener to this point. So if you say the thread is 1 inch long, then this should represent an inch. This doesn't necessarily, even though they may have some dimensions here that say, well, this represents the minor diameter or the root. If you're going, you know, if you're looking at it that way, and this represents the crest or the major diameter, nobody is, you know, nobody does that to an accurate distance. Usually, when you draw it, especially if you draw it by hand, if you put a chamfer on it like this, this is where you start that dotted line, the hidden line. You usually start it right there and just draw it out to wherever you need to, and that's that. Because it's simplified. It's not meant to really represent any of that, you know, those dimensions of the thread. It's just a quick way of showing threads because nobody wants to take the time to do all this, especially if you're doing it by hand, or this for sure. Try drawing that out, you know, a couple of dozen times a day. Pros and cons of the detailed view. Looks good and clearly represents the thread, but it takes a long time to draw. Schematic. It's almost as effective as the detailed view, and it's a little easier to draw, but it still takes a lot of time. So yeah, they're still showing the minor and the major diameter, the thread length, and the pitch. Schematic should not be used for hidden internal threads or sections of external threads, or sections of external threads. And why is that, do you suppose?
I think the lines could become too confusing.
Yep, that's exactly the reason why in my mind, is that it just becomes way too confusing. So that's why everybody draws simplified views. The thread length, again, like I said, is from here to here. It's simple and fast to draw, but it doesn't really look like a thread. But if everybody knows that that's what it's supposed to be, then it looks like a thread. You know, you look at you know, a few drawings in a day that are, you know, that have some hidden, you know, or have some threaded external or internal threads, and you'll get the message. The only thing that I don't necessarily always subscribe to is this view with the hidden lines, because a lot of places I worked wanted you to draw this line as a solid line, because in effect, when you section this part in half, you're going to see the major diameter and the minor diameter, or the root and the crest. So generally speaking, most places I've worked wanted this to be shown as a solid line. Does that make sense? To me, it makes sense because, like I said, if you cut a part in half, you're going to see that, you know, threaded hole or threaded, solid cylinder. You're going to see the root and the crest. So I've always drawn on where both these lines are solid lines. But if you do it this way, it's okay too. That's it. Not too bad, right?
Nope.
No. So this note, we're finishing the P311 as homework anyway, because we can't do it in class. So we're good. That's it for that. The assignment that's being given to you today is this chapter 8.8, 8.11 preview, and all that is answering
3 questions.
Yeah. 4 questions, or yeah, 3 questions.
3 questions.
Yeah, 3 questions. I can't. You obviously did it already, and
Yeah.
I obviously can't read. Yeah, it's nothing. It's nothing major. So I'm trying to wind it down, for as much as we can for the remainder of the semester. Hopefully, it gives people a chance to catch up. That haven't caught up. Okay, so let's talk about this online SolidWorks situation, because I think some people are having trouble running it well. And here's the deal. So this is the announcement that I put up back in January about the link to using SolidWorks Online. So if I select that link, it's going to ask me to sign in here, and I think I'm already signed in here. So I just have to put in my school ID and password, and then I can go to AppStream because I want to use SolidWorks AutoCAD, and say sign in, and now it's going to give me this. It's going to give me this screen, and if I go to SolidWorks 2019, it'll start to do the SolidWorks load. What I want to show you is this thing down here. It says AppStream 2.0 Client. If I select that, it talks about the browsers that it is supports. But if you look over here, it says Windows Client Download. If you do this instead of the normal method of getting signed on to AppStream, if I download this guy and run it, what's going to happen is instead of running through a browser window, it's going to load this client on your PC. Hang on just a second, because I got to get to it. It's actually on my desktop on the other side, on the other on my other monitor. So I'm going to close this tab out, and I'm going to show you that here's what what it looks like. You can all see my desktop, my cluttered up desktop right now. So this is what happens. It downloads this client and creates a desktop icon. And if I double click this guy now to run it, see how it runs? It doesn't want to run in a browser window. So it gives me this information. I just say connect. And then I have to do the same thing in terms of my password. And now my password generator doesn't work for this. At least not yet. We'll see if I could have maybe right-clicked it, but And it's the same look to signing in, right? Once I did that, I'm at the same screen. But notice I'm not in a browser window. So if your browser is not, is having issues running this, you're bypassing it. So I go to AppStream, SolidWorks, AutoCAD, say sign in, and again, running in a window on my PC, not in a browser. So I say, oh yeah, let's go with SolidWorks 2019. So it looks a little different in terms of the sign in. I haven't used it in a while, so we'll see if I run into any issues, which might not be a bad thing. So hopefully we get them resolved while we're doing this versus having 20 questions later. Unfortunately, it doesn't really load any faster this way. It still takes a couple of minutes to set up the session. And notice I've got the P311 part and the drawing, the C size. I put those on my desktop too, so I could bring them in and show you that works. Basically the same. I don't think it's any more or less streamlined. And hopefully this thing will load up instead of saying, hey, it's taking too long. So again, I get to this point, and one more time I have to put in my password. Perhaps I typed it. Let's see. Yeah, but I bet I typed the wrong password. I have a tendency to modify, my passwords by one or two characters. Yeah, that's what I did. I just typed in the wrong one. So it starts up just like regular SolidWorks, and just like it does within the browser. But again, there's none of the browser toolbars up here. So it eliminates having to work through a browser, which in my mind, every time you go through another portal, you're losing something. Mm-hmm. And when you look at it now, other than this one toolbar, which is the AppStream toolbar, which you have to have, it looks a lot more like a normal SolidWorks interface, doesn't it? So now I want to open those two files, the part and the drawing, but I can't just go say, I don't believe. I can't just go to my local folder, my local desktop, and say, hey, I want to, I want to open those. I still have to bring them into AppStream. So I have to go up here and look at my files and go to the home folder. And this is all I have in there. I need to upload, I still need to upload the files. So I still need to upload, and now I can go to my C drive. Go to my desktop and hopefully find those P311 modified part and the C size. See if I can do them both together. C size starter drawing. Yeah, I can. See, I picked one and then held down control. I found the other one and held down control and selected that. So I should be able to upload both of those at the same time. And there they are. They're in my home folder. So now I can say, okay, I can close that out. I can go back to SolidWorks and go back to my home folder in SolidWorks, and there is the part, which you can't see a preview of, and there's the drawing. So I'm going to open them both together. I can do that too for the same way. Just pick one, hold down Control, pick the other one so they're both highlighted. And I should be able to open them both at the same time. And the command manager pops up. It says it can't find the font that so I'm using the standard installation of the local version of SolidWorks loaded on my PC. I never changed any fonts or anything like that, but it can't find Arial Narrow. So let's go, and rather than use a replacement, I'm just going to say, hey, let me find Arial if I can. Because if I use a replacement, who knows? Maybe I'll use a temporary after all, and just see. Because maybe what it'll do is it'll hopefully revert back to the correct font when I re-download the file. So now I've got two files open, and that's why I've got two windows working inside the SolidWorks window. All I need to do is say, hey, I want to maximize one of them. And there's my part. And you see, I opened this stuff. I added these toolbars after because they're not part of the standard setup. So one of the nice things about this, I'm assuming going through the browser does it for you as well, is that once you make some modifications to your interface, like adding toolbars, the next time you open up the interface, it should show those same toolbars open. As you recall, I've always, when we're in class and we get that vanilla install every time, I always add the standard views toolbar and the standard toolbar, so that I've got some information there at my fingertips. And you see, I did that, and now it's always showing. So it modified the setup file so that it includes those toolbars every time. And then I can go ahead and I should be able to do a Control Tab and switch between open documents. And here's my drawing. And then if I say, hey, I want to bring in some views of that part, hopefully it'll show up here, and it does. P311 modified. They're both open. They're both in the same folder. And then I can bring in my views like I did before. But it's a cleaner, to me, it's a cleaner interface than it is going through the browser. Unfortunately, it only works for Windows. If anybody has a Mac or Chromebook, it won't work. There's no client to download to run. So you've got to have Windows in order to use that client. And I got a notification here. I think this is just my downloads notification that I downloaded or uploaded those two parts, I should say. Downloads, haven't done any downloads yet or printed or do anything like that. So that's all this guy is just notifications. But again, I've got, the rest of the, all the commands at my fingertips here. If I want to create that extra view, I can say, I want to do a projected view from that view right there, like I did before. I can bring it down here a little bit. I can crop it just like I did, and a crop command wants you to draw some kind of a sketch first as to what you're going to crop, use for your border to define the crop. And then I go back to view layout and say I want to crop that part, and then it crops it based on my sketch, and then I can go ahead and dimension this guy just like I did before. Apparently not. Now we can. And I still can't grab that outside circle for some reason. I don't know why that is. But, and so and then I have to go through the rest of the, let me put this other dimension on here. Let's see what happens. Now that it jumped out here, will it have a leader? It does have a leader. Remember the other day I couldn't, if I put the dimension out this direction, it wouldn't show a leader here. So anyway, I can do everything that I did, and I can also go ahead then and check my units and make sure they're where I want them, and set up my my drafting standard and make sure that that's correct. Look at my dimensions. And make sure that all of those, the base diameter dimension standards match my overall standard of ANSI, so that nothing is different. Because if I go with my linear dimensions and say that I can change this to ISO, right? And if I do that, that one linear dimension, these linear dimensions are going to look like ISO dimensions now, which I don't want. So if that's the case, if they look like this, and you go back and check your your drafting standard, and it says it's ANSI modified, then look at the linear dimensions and see if there's an issue with the base standard for that particular type of dimension. If it says ISO, then change it to ANSI, and then you should be good. I'm going to section this guy also. And I'm going to replace, I can't replace the front view. So I'll just add it. Because there's something else I wanted to show about the section view in case it was not clear enough in the instructions for like the P39. I didn't grade on it because I didn't really demo it in class. So let's do a section of the part, even though we're not supposed to. And I'm going to section it right there. Bring this down here like this. I showed you guys how, I did that video to show you how to change the section lines. So, but I'm going to change them again just to double up on that. If I select the section line, I don't think I have to select this one, as long as I got one of them highlighted so that I've got the property manager up. You see, this is not basic. It's based on material, but it's still just an area. It's called an area hatch or fill, because if I change it, if I could change it and change it to solid, it would be solid. But I can't change it because right now it's saying, hey, I'm showing section lines based on the material of the part. So right now the part has no material. If I go back to the part and I give it a material, see, it's not specified. If I right-click material here, I can select from some of the stuff that's on the favorites list, and I can add, definitely add materials to this list. So let's go with plain carbon steel. Okay, and notice the part look changed because now I've got a material assigned to it. If I were to assign ABS plastic, well, now it's going to look like clear ABS, right? So you can see through it. You can see all the, you know, the lines of everything because it's clear polycarbonate. That's what the ABS PC is. It's polycarbonate. If I change it to brass, now it's going to look like brass. And again, if I look at the drawing, can't find my cursor. My section lines changed because they are tied to the material of the part. If I want to change them independently of that, then I have to uncheck this, and notice now this all became bold. I could make it solid if I wanted. I don't know why I'd want to do that. But right now, I'm still showing the brass, but I don't know what did do you remember what the part, what the P39, what that material was? Let's just go with aluminum. I'm going to change this.
It was steel.
Steel, that's fine. I'm going to change this to aluminum. So, which is what I did in the video. So now that I got this unchecked, I can change my material call out on the drawing without even knowing what the material of the part is. And if there is a material, the reason it defaults this way is because we don't want there to be a conflict between the material that you're showing on the drawing versus the material that is called out in the part, because that's probably what the designer wanted. But if there is no material called out and it doesn't matter and you want to call it out specifically on the drawing, you can deselect that, go back up here and say, this is brass right now. Let's make it aluminum. And so now the section lines change to aluminum, but it didn't affect the part. Didn't change the part to aluminum. It just changed the area hatch or the section lines on the part. Okay, so that's basically what I did in the video. The other thing that the drawing or that the instructions for the P39 asked you to do was to change this cutting plane line, because right now it shows as a dotted line, and you want to change that. Well, you can't do it. I can't do it here. I can highlight this, but there's nothing that gives me any way to change what that section line looks like. So the instructions for the P39 said go to either go to document properties that way, or the other way to do it is to go to the settings tab here and go to document properties, and then look at the views, and then go to section under views, and here is the line style information. And it says to change this dotted line to a phantom line, right? Change that to a phantom line, and then change the thickness to like 0.138. So that's what I did right there. I changed the thickness and the style. And I could also change the way the arrows look if I want, but this is kind of standard. I could eliminate that line that runs through it and just show a section line from here on the other end as well. Kind of just show this much of it and that much of it, but kind of like having the section line cut all the way through the part. And then if I say okay, see that now the section line updated, and it's a phantom line, or it's a cutting plane line with a thickness that's a little heavier than everything else, which is what it should be, right? That should be, the cutting plane line should take the precedence even over object line or a solid line. So that's how you do that. You don't have to do this for the current project, the P311. You don't have to show a section view, but you'll probably have to show a section. We have one more project drawing, and then I'm not saying whether or not you'll need to do it for the final. That remains to be seen. So that's how you use this, the AppStream client, and then that's also how you modify section view to show different material in the drawing and then modify the section cutting plane line. And don't forget, whenever you do a section, that your view should always be opposite the direction the arrows are pointing, right? For third angle projection. So that's why this went down here. It's just the same as looking at the front view of the part, only the front view is cut in half, right? It looks exactly the same, except for the tangent edges. If I get rid of the tangent edges, it'll look even closer to being correct. But see, now I can see this slot here. So I can, if I didn't need this top view to show the depth of this thing, I could show it in this view, but I don't need to do that. Make sure that you're showing your center lines. And again, what have I got here? I got tangent edge and center line, and that tangent edge is kind of interfering, right? Because it's a slot. So that tangent edge is the point where the radius and the straight line meet. So I could do the same thing I did in the front view for the section view. I could highlight it and right click it. I'm still in the center line command. That's why. So I can right click the view and say, hey, I want to get rid of the tangent edges. And now they're gone. And you can see the center lines. Any questions?
Nope.
Mike, are you good?
Yep.
All right. I think that's going to do it. What did I just do here? Before we go, let me go back to sharing because I want to stop my recording. So if you have no other questions, let me zoom back out. Then I think that's it. All right. Stopping the record.